Okay, so if you look at the new packet that had you pick up, we're going to get started with the AP review packet. So we're taking a day break off from reviewing. We are still going to have another full day of review next Thursday before your quiz, which is next Friday. So this calendar starts off next Thursday. And we're going to have we're going to start going fully into AP review. So today we're going to do the first day of antiderivative word problems. We're going to hopefully get through problems 1 and 3, and then the rest of the pages and their assignments will be highlighted in your new calendar. So each day, I'll give you a solution key as well, but each day there's going to be assignment that is due, and each assignment is worth 5 points. Basically, it's going to, packets 1 and 2 are going to add up to be 50 points. And then your assessments will be the other 50 points. And that will add up to be a 100-point test grade. So, half your grade is, yeah.
Is it just like normal tests?
Well, I'll show you exactly what it looks like. It'll, we're going to work towards, if you look on page 21 it's very specific type of FRQ. So, so before we get there, it'll be, you'll know exactly what to expect. Okay. So, we'll have, after we get back from break, we'll have a full week to prep for that FRQ. Okay. And then, yeah, some of the things after spring break, I may adjust a little bit, but essentially, we're going to be working towards a second FRQ quiz. This is, I said FRQ test, but this one will be a quiz. Just be over Riemann sums and differential equations. And then before May hits, we're going to have multiple choice tests, or multiple choice tests split up into 2 days. And then after that, we'll do some more AP review. And then by then it'll be May, and we're going to be taking the AP exam May.
Would it be an over assessment?
I'm sorry?
Would it be an over assessment after the
No, these will be the last ones. Well, there will be assessment, but those will be take-home assessments. And so you just have to do completion, and you'll get like quiz grades for them.
How many review periods we're going to have in total?
We're going to have 3 that we're going to prepare for these quiz and tests. So each quiz and test will have its own, I guess, separate packet to review from. And then I'll give you 2 additional ones just for you to work on and turn in before the end of the school year. Which will just be old FRQs and old multiple choice tests for you to just see, get some reps with what the problems could look like on the exam.
I know seniors like their last day of school, like before the actual exam. We turned it in by that last day.
Right. Yeah. That's the hope. But I think we have teachers have some flexibility in terms of the grades aren't due for seniors until like a few days after that. So, but ideally, yeah, if you're a senior, you can turn it in before your last day, so that we can just get that out of the way. Right. Okay. So let's go to page 1. You're going to need your calculator. Right. Okay, just a little bit of a review in terms of units of measure. So anytime we take the derivative or integral, we know that our units will change because we're doing something, we're making some drastic changes to what we're working with. So if our velocity is in meters per second, then we know that v prime is going to be derivative. Derivative is we're going to have to include another rate. We're adding another rate there. So velocity becomes acceleration, which turns into meters per second squared because we're applying a derivative, which is the rate of change, and rate of change is slope, and slope is change of that unit divided by change in time. And if we're dividing by change in time, we're adding and we're making some changes to our units. Likewise, if I take the antiderivative of velocity, then velocity will turn into meters, will turn into displacements, right? Displacement is in terms of if we're starting with meters per second, then our new units will be meters, since the accumulation of the rate, basically finding the area under the graph through integration, will result in a new unit of measure, giving us displacement. So for instance, if you're traveling 60 miles per hour over a 5-hour period, this doesn't require calculus, but it's the same idea that if we're accumulating this rate over a 5-hour period, then what we're left with is a different units, right? If you travel 60 miles per hour over a 5-hour period, it doesn't turn to 300 miles per hour. It turns into 300 miles, right? 300 miles per hour, that doesn't make sense. This is, we're taking that rate and accumulating it. So if you're accumulating a rate, your units will change. If we're to do this in a calculus sort of way, then it doesn't need calculus, but if we were to make this calculus problem, you would say the integral of 60, if 60 is your velocity, then if you're accumulating that velocity, 60 becomes 60t. You plug in your upper and lower bound, you get 300, and then the displacement of that rate over the change of this 5-hour period will still get you the same answer. Okay. So I want to keep reminding us that integral will change your unit. It'll strip away that time component, and your derivative will add a time component. It will divide by another time unit. Okay, so let's look at example one, problem one here. We call this antiderivative rate in, rate out problems. Because there's going to be multiple things going on. You have an accumulation of something that's being added, and then you have something that is being removed. And we have to kind of make sense out of both those things. So this has been a popular type of FRQ problem or category in recent years. So want to make sure we spend time going over these types of problems. I'm sorry?
Have you gone over?
Right, we haven't, well, we understand what integral does, but we haven't quite seen these types of problems per se. So so I wanted to kind of make sure as our first day of AP review that we cover this kind of pseudo new topic. Okay, so the rate at which people enter an amusement park is modeled by the function E, which is given by E of t. So it looks like a complicated equation, and we can make the calculator do it for us. But basically, this is saying that over the course of the day, E of t can change, right? So for instance, at the beginning of the day at, let's say, Six Flags, for instance, on a Saturday, your rate at which people are entering into the park at 9 a.m. is going to be really high, like maybe like 200 people per hour, just making a number up, right? And then that rate will probably stay pretty high until, what do you think the rate of people entering in the park will be come like mid-afternoon?
So
Decrease, right? Maybe like 10 people per hour, right? Because most people are not going to be coming in to the park that late. And then what do you think the rate of people entering the park at 5 p.m.?
Not very many.
Right, not right, especially if the park closes like, early evening or something. So we can kind of imagine, what that EFT is doing, right? Starting high and it's going to come down low because the rate at which people are coming in is going to be different over the course of the day. Okay. And then L of t represents the rate at which people are leaving the park. Okay. What do you think L of t would be at the beginning of the day? Very low, right? There's probably not many people leaving the park at 10 a.m. In the morning. But the rate at which people are leaving the park at the end of the day is going to be pretty high, right? Because people are going to start exiting the park, and it's going to be like 200 people per hour or 300 people per hour. Okay, so that's the idea, that we're kind of playing with those two rates. I want to give you those numbers so you can kind of visualize what could be happening over the course of the day. Okay, both EFT and LFT are measured in people per hour. So again, this is a rate. That's what we said, per hour, 200 people per hour, or 10 people per hour, or 0 people per hour, in hours after midnight. These functions are valid between 9 and 23. So that tells us that the park is going to be open between 9 a.m. and 11 p.m. Okay, military time. At 9, there are no people in the park, okay, or there are no right. So there are no visitors in the park at 9 a.m. So part A says, how many people have entered the park by 5 p.m.? So if we have the rate at which people are entering the park, what do you think we can use to help find the number of people in the park? Yeah, antiderivative, right? We're going to accumulate that rate over the course of the number of hours. And we know that, whatever the rate is times the hours will just turn into that numerator unit. So people per hour through integral will turn into number of people. So we're just going to set this up here. Have entered the park by 5 p.m. So what do you think our bounds will be? 9 to 17. Yeah, they tell us P equals 17 represents 5 p.m. Okay. So again, I want to show that the units are changing because E of t is in terms of people per hour, but technically we're multiplying by dt. dt is a time unit, so times time, so people per hour times time will turn into a number of people. So we're going to make the calculator do the work for us. You can go to y equals and you can type in your EFT, your messy EFT, which tells us the rate at which people are entering the park. I would do this though. If you do alpha y equals, you can get that n over d to show up. If you have an older calculator, you're going to have to do big parentheses for both the numerator and denominator. You're not going to have that luxury of having that clean math print that looks just like what you see here. Okay. Okay. What variable are we going to use in our calculator? X, yeah, always X, even though you may see different variables on paper, you're going to be using X. If you do alpha trace, sorry, my bad. Alpha y equals, you'll see that n over d. Okay, we can exit out, do a second mode. Now you do math 9. From 9 to 17, alpha trace y1 dx. Okay, so we'll just round down. I guess if you round down and round up, in terms of people, that's acceptable. But I'm just gonna round down and say it's about 6,004 people are going to enter in the park by 5 p.m. Okay, so note the change in units, right? We started with people per hour. The integral process will turn that unit into the number of people, because E of t is people per hour, and you're multiplying by time unit times hour. People per hour, hours will cancel out, so that's why we have left with people. Okay, questions so far? Part B, the price of admission to the park is $15 until 5 p.m. After 5 p.m., the price of admission to the park is $11. How much money is collected from admissions to the park on a given day? Round your answer to the nearest whole number. So basically, we can figure out how much money is collected by doing this, right? Let's find out the number of people who've entered in the park by 5 p.m. Then we can do what to figure out how much for that group. Yeah, multiply by 15, right? And then separately, we can find the number of people who've entered in the park after 5 p.m. and then figure out how much we're going to collect from them, which is $11 per visitor. So we can use this value, but I'm going to write it all in integral notation and then kind of put it all together. So we say $15. We're charging $15 for each of the people that we are going to that's going to come in through the doors or coming through the gate. So this will tell us the revenue from the people who've entered in the park by 5 p.m. And then plus, I'll put dollars here to indicate that. And then we'll charge $11 for those who've entered in the park after 5 p.m. So we can say the integral from where to where, from where when to when. 17 to 23. So this is basically 6,004 times 15. We can figure out what that number is, multiply that by 11, and then enter this in. Okay, so this is how much money the park can bring in on that day based off of the formula or our integral notation there. Okay. Part C says, let h of t be the integral from 9 to t, this is some unknown t value right now, of v of x minus L of x between 9 and 23. The value of h of 17 to the nearest whole number is 37.25. Find the value of h prime of 17 and explain the meaning of h of 17 and h prime in the context of the amusement park. So let me break this into, and then if you run out of room, we can go into number 2. I don't think we're going to do number 2, so well, at least it won't take up that much space. We can use the bottom half of number 2. Later on, it'll be for homework. Let me break this. Let me write out h of t here.
Why did you change the 1722?
Oh, because this is going to be the number of people who've entered in the park between 9 a.m. and 5 p.m. And then the group of people who've entered in the park between 5 p.m. to close, they're going to be charged a lesser amount. Yeah. So number of people times $11 plus number of people times 15, and that will tell us how much money the park is bringing in. Now notice the variable has changed. It went from t to x, but it represents the same function. It's just that we need this to be inserting into a different variable, so that's why it's changed into x. Well, that's why they changed it in terms of x. So to help us kind of understand what's going on here, what if we break these two things apart? Because we can, because there's a minus in between. This is the same thing as saying the 9/17 of e of x minus integral from 9 to 17 of L of x. Let's look at this separately here. What do you think this represents? Okay, the number of people who've entered the park. And what do you think this represents? Number of people leaving the park, number of people who left the park or exited the park. So if we have the number of people who've entered in the park and we subtract the number who've exited the park, what does the resulting number tell us in the park? Okay, so h of t. So sorry, the 17 has not been inserted yet, but it will. So t is flexible. It can be any value. We can figure out that's the formula, right, up to that time. So what do you think h of 17 is going to represent? Number of people left in the park. What does that 17 mean? At 5 p.m. Okay, good. So we're going to find that value. Yeah, it says, sorry, they did tell us what that number is. The value of h of 17, so the nearest whole number is 37.25. So that 37.25 tells us the number of people left in the park at 5 p.m. Right? Because we've found all the numbers who've entered, we've subtracted all those who've left. So what's left over are the people remaining in the park. So h of 17 equals 37. So 3,725 visitors left in the park. Okay, so that's the first part of C. Next part, find the value of h prime of 17. So h prime of 17 means we got to take the what? Derivative. Let's do h prime of t first. Let's build the derivative and then we can work in the 17, right? So I'm gonna do h prime of t. So if I want to find the derivative of this, what do you think is needed here? Do you guys remember? Oops, not 17. We're asking to find the derivative of an integral. What's going to happen here? They cancel out. This is second theorem, right? Basically applying second theorem here. So these two wipe each other out. The upper bound gets inserted into the variable now. So h prime of t is just e of t minus L of t. Does that make sense? So we're just applying second theorem. Second theorem says derivative and integral are opposite operations. They cancel each other out. We just have to replace the upper bound into the variable of the expression. So h prime is simply e of t minus L of t. So if I do e of t minus L of t, what do you think that information is going to tell us about what's happening?
The amount of people that are currently still.
Well, this is a rate though. This is not the integral anymore. Integral is the number of people. This is going to be the rate at which people are
In.
Yeah. Okay. So
It's in the enter and exit both cancels over out.
okay. Yeah, to some extent, right? So what do you expect E of t to be at the beginning of the day?
Higher.
Higher. L of t is going to be
Lower.
lower, right? So we know that h prime is going to be a positive value at the beginning of the day because this is basically telling us the rate at which the park is growing. Is it growing or is it decreasing? The rate at which the people in the park is changing. So at the beginning of the day, E of t minus L of t is going to be high. Okay? And then at the end of the day, what's going to happen to this number?
It's going to be negative.
It's going to be negative, right? There's going to have like a low E of t followed by a high L of t, and it's going to be a negative number. Okay, so let's go ahead and do that. H prime of 17. What do you expect out of H prime of 17? Negative, probably, right? Most likely, assuming that it's a normal day and there's not some special event going on at night. We expect, more people to be leaving than coming in, and so the rate at which people are, the rate at which the number of people in the park is changing is probably going to be negative. Okay, so let's make the calculator do that for us. So I'm going to have the calculator right now. Y1 is holding E of t, and then I can have Y2 hold L of t. So again, I'll do alpha y equals 9890 divided by x squared minus 38x plus 3. So okay, going back to my home screen here. If you do alpha trace y1, this is basically holding my E of t. If I do parentheses 17, then it's just going to plug in 17 directly into all the variables for me. So that's nice. So this is basically just going to be my E of 17 minus L of 17. Okay, alpha trace y2, parentheses 17. Give me a messy fraction. I prefer a decimal here, so I'll do math fraction. Sorry, math decimal. So we get negative 380.28. The units is still going to remain the same. It's still people per hour. So this tells us that at 5 p.m., the number of people in the park is decreasing by 380 people per hour, right? And this sort of makes sense, right? That the population in the park is going to be decreasing because more people are going to be leaving than coming in. Yeah.
Was B question?
Yeah. Okay, so basically that negative 380.28 people per hour means the number of people in the park is decreasing at a rate of 380 people per hour. Okay, running out of room here, but I think the last part won't require a whole lot of room. Okay, part D. At what time does the model predict that the number of people in the park is at a maximum? Okay. So what do you think if you had to just have to guess, when would you expect the park to be at a maximum on a normal day at an amusement park?
Like noon.
Noon
11.
or early afternoon, something like that, right? Somewhere in that, definitely not early morning and definitely not late afternoon. It's gonna be somewhere in between, right? So somewhere maybe noon to early afternoon. That's probably gonna be most people's guess. Okay, so that's what we can kind of expect. So how can we use EFT and LFT to help us decipher when that maximum number of people in the park is? Right, so let's think about that, right? So EFT, we know EFT is going to start high and it's going to decrease. LFT is going to start low and it's going to increase. So this is what's going to happen over the course of the day. So when do you think the maximum number of people is going to occur? Yeah, it's when they are at the same level, right? When they meet, right? Because after it goes to this, where LFT is higher, then more people are going to start leaving and the park is going to start decreasing after that, right? So the park's going to increase up until this point, and then once LFT overtakes EFT, then the park is going to start shrinking. So the idea is the number of people is going to be at a maximum but also this is when the rate of change is 0, right? We know a positive rate means more people are still coming in, that we haven't reached a maximum yet. So basically when H prime is equal to 0, like you said, when the rate is 0, that's when EFT and LFT will be the same. So the maximum number of people will occur when H prime is equal to 0. Thank you. Okay. Well, how can we make the calculator do that for us? Because we don't want to do the algebra to figure out when those two are equal to 0. So this is what we can do. We have EFT being held under Y1. We have LFT held under Y2. So what if we do this? What if we graph this equation and just figure it out where it crosses the x-axis? If we graphed this and look for the x-intercept, then that we can figure out the time when the maximum number of people are in the park. So we're going to make the calculator do that for us. So under Y3, I'm going to have Y1 minus Y2, and then just graph it and look for the x-intercept. So I'll do alpha trace Y1 minus alpha trace Y2. And as I do that, I want to unhighlight Y1 and Y2. You see how equal sign is highlighted? I don't want to see those two graphs. It would just make things more complicated. So I'm going to hit enter on the equal sign, which means that I'm not erasing the function. I just still want to see it on my graph. I just want to see my Y1 minus Y2 graph. Now, however, you notice how my numerator is at such a large value. These are basically my my y-intercepts. So I basically want to make sure that my window is in the thousands. Doesn't have to be exactly that number, but let's make our y value in the thousands because The graph, otherwise our graph is gonna be so zoomed in, it's gonna look like a straight line. We're not gonna see any curve to it, and it's gonna be hard to we're basically zoomed in too far. So let me just make this like negative 2000 to 2000. Maybe it may be enough, it may not be enough, but we can, and then we know our x min, x max, we can go from, let's say 0 to 30 because, you know.
This graph's gonna be like really zoomed out.
Huh?
This graph's gonna be really zoomed out.
Right, but also our graph is really big as well. So we want to kind of adjust that window. I'm going from 0 to 30 because 24 hours in a day, it's going to be from 9 to 11 p.m. But that's just an easy number for me to choose. Let me just hit graph. I just need to make sure that there's some curve to it. So that's good, right? And if I can find that x-intercept, I can figure out the time in which the maximum number of people is going to exist, right? I have E of t minus L of t. I'm just looking for the x-intercept. That's when my slope is going to be 0. Okay, so if I do alpha trace intersect, sorry, 0, because I'm looking for an x-intercept. Pick a point to the left of the x-intercept, hit enter. Scroll over to a point on the other side of the x-intercept, hit enter. Hit enter a third time. So 15.79.
So all the positive values, like ET, and all the negative values are LTs.
No, this is E of t minus L of t. So whenever the graph is above the x-axis, that means the number of people in the park is still growing.
Okay.
And then once it hits below the x-axis, that means the number of people in the park's decreasing. So we want to be able to know, hit that exact x-intercept will be when that maximum is going to occur before it starts decreasing.
Why does the number of people that are decreasing, why does it go back up to the end? Is it because like less people are leaving?
Right. So this part just means that the number, there's less and less people at the end of the day. And so the rate at which people leaving the park is going to be decreasing, right? Because there's not much people left in the park. You know, by the end of the day, it could only be like 10 people per hour because most people probably don't want to stay till 11 p.m. at night. Yeah. But it's still decreasing, right?
Yeah, it's like at a less rate.
Right, at a lesser rate. So we can say that t equals 15.794 is when the maximum number of people is in the park. And that's going to be around like 3 p.m.-ish, right? So that makes sense, right? In that early to mid-afternoon is when we would expect the park to be on a normal day to when the population will be at its maximum. Okay, so we spent pretty much the whole period on this one problem, but next week, next Thursday, we're going to do quiz review. Next Friday, we'll do the quiz, and then the following Monday, we'll continue with this, and we'll just kind of continue to get comfortable with these types of problems. We'll do a few more of these. We'll spend another day on these rate in, rate out problems. Okay. All right, come get your phones.